In this video, we are going to be looking at the limit of a function. In the last class, we were considering how a secant line eventually becomes a tangent line by taking this limiting idea of bringing 2 points closer and closer together. We're going to formalize that more in this section. Let's consider the function x squared minus x plus 2. And I've got a graph over here on the bottom right-hand corner. And we want to consider what's happening when we get very close to x equals 2, but not at x equals 2, just approaching from, let's say, the left side coming up here, and then also approaching from the right side coming down here, right? We want to know what's happening right at that exact point. The tables that you see on the left-hand side are picking x values that are getting closer and closer. The table here on the left is approaching from the left-hand side. And I'll put LHS. And the table here on the right is approaching 2 from the right-hand side. We're getting closer and closer to 2. Looking at the output values in both these tables, it looks as though both of these values are approaching 4. Well, we know that if we were to plug 4 into this, or sorry, 2 into this function, if we were to take, let's say, f of 2, we'd have 2 squared minus 2 plus 2, which is in fact 4. So it makes sense that the output value that we're getting from looking at the limit from both sides, is 4, because that's what the function value is. That's not always the case, though, because in examples we'll see later, we might have a limit where the function isn't defined at the particular point in question. The main thing to take away from this slide is that we're going to start thinking about how limits are working, looking at approaching from 2 sides, the left and the right, simultaneously. If we have a function that's defined where x is near some number a, meaning if I had a number line, let's say like this, and I have some function, some value a, and I consider x's anywhere in this region, anywhere around a, we're saying that the function, whatever it is defined in this area, right? The reason it needs to be defined is so that we can think about the function or the limit coming from the left and coming from the right. It needs to be defined within this certain region. The notation that we use is here, the limit of the function as x approaches the value a. We're going to pick values of x that are closing in on this value a. And we get some output value. We say the limit of f of x as x approaches a is equal to L. We're going to get closer and closer, but not necessarily know what's happening directly at that point A. There's a lot of text here, and I want to come down to show you a picture of what this is talking about. It's talking about how the y values are changing as the x values are changing. That we have the y values closing in on a particular value as the x values are closing in on a particular value, in this case a. So here are 3 pictures of what we're talking about. L is the output value for the function, right? We're going to call that the limit. In the first example, the function is completely defined at the point A, right? We can see that it's continuous. In the second example, the function is defined at the point A, but it's not defined at the point where the limit seems to be approaching from left and right. And then in the third example, the function is not defined at that point. We have an open circle there, so there's just a hole in the graph. In all 3 of these examples, however, what we're asking is what happens as we approach from the left and also from the right. Looking at this first graph, well, I am approaching the same value, L. Looking at this graph, I am approaching the same value, L. All three of these have the same limit, even though the graphs are defined differently, the functions are defined differently. The point is that we can say that the limit exists regardless of whether the function is defined at that particular point. Here's an example. Let's consider the limit as x approaches 1 of this function, x minus 1 over x squared minus 1. We know that this function is undefined at 1. It's not allowed to equal 1. We have a hole. We can see over here we've got a hole in the graph, right? If I plug 1 in, the denominator is going to be equal to 0. So that's why the function is undefined there. But it doesn't matter that it's not defined, because if we were to take values of x that are close to 1, here we're getting closer and closer from the left-hand side, and here we're getting closer and closer from the right-hand side, both of those output values are looking like they're approaching 0.5, right? What we'll talk about in the next section is how we can use algebra to analyze these functions differently and decide and convince ourselves mathematically that the limit is in fact 0.5 without having to have a picture of a graph and without having to make this table. We don't want to have to plug in a bunch of values like this to determine what the limit is. So we're going to work towards strategies that simplify this process. Let's consider a piecewise function. Remember that a piecewise function is one in which we have maybe two or more different definitions based on different domains or different sections of the graph. In this particular case, this is the same function that we had before. So it's defined as this x minus 1 over x squared minus 1. But at the point of discontinuity here, we're going to give a separate value. We're going to define it to be somewhere else. It doesn't matter that the function is defined to be elsewhere when we talk about the limiting value. We can see from these pink arrows here on the graph that we're still approaching the limit of 0.5, even though the function is defined in a different location. Because we can have discontinuities in functions, and because we can have what we would call a jump in a function, like the picture you see here, we have to sometimes consider what's happening for the limit as we approach from the left versus what happens as we approach a limit from the right. Look at this notation down here. We've got this superscript. It sort of looks like an exponent on the 0. T is approaching 0 from the negative side. So this is from the left, right? And here we have a T approaching 0 from the positive side. This is going to be from the right. When I'm saying positive and negative, I'm meaning positive and negative on the number line, like this. Looking at this function, as I approach t from, if I approach 0 from the left-hand side, the function output value is 0. That's what I'm getting here. But as I approach from the right-hand side, the function output is 1. So we, in general, will say that the limit overall doesn't exist. Notice that here we don't have a plus or a minus as a superscript. We just have what's happening at the point 0. Because those limits are not approaching the same number from left and right, we say that the limit doesn't exist. So sometimes what we'll do is we'll talk about just a one-sided limit because maybe our function isn't defined beyond a certain point. And that's okay. In this first picture, we're talking about approaching this limit from the left-hand side. That means we're taking points that are closer and closer to A coming in from the left versus here, this is approaching from the right-hand side. we will say that the limit exists overall only when both, oh, sorry, not that one. Here, the limit exists if and only if. It's only going to exist if we have the left-hand limit equaling the right-hand limit. These two have to be equal to say that the limit exists overall. Let's do an example problem with a function that's sort of defined in a funky way. We've got a couple different discontinuities here. We've got a jump. What is the limit for letter A? What is the limit as x approaches 2 from the negative side? So we're looking at this, and we're approaching this way from the left. So it looks like the function output value is 3. That's what we have here. Let's look at letter B. Letter B is asking us to approach 2, but this time from the positive side. So the function output value is 1. Looking at letter C, we're wanting to know what is the limit as x approaches 2. When we don't have a plus or a minus, it's asking us for the overall limit, and we have to say that it does not exist because the left-hand limit and the right-hand limit are not equal to one another. Moving on to problem letter D. What happens as we approach 5 from the negative side? So coming here, the output value is going to be 2. So that's the limit. As we approach 5, letter E, as we approach 5 from the right-hand side, we're also still at the same output value of 2. So when we want to think about analyzing the limit overall, we can say that the limit as x approaches 5 is equal to 2 because both the left-hand and the right-hand limits are equal to each other. Even though the function is not defined at that same location, right? The output value when we're at x equals 5, the output value is y equals 1. But the limit is approaching y equals 2. We can also have limits that are infinite, that they're not closing in on a particular value, but they're going up to positive and negative infinity. In pre-calculus, you probably looked at some rational functions where you had these asymptotes all over the place, and we had functions shooting up to positive infinity or coming down to negative infinity. So these would be two examples. In this first example on the left-hand side, we can say that the limit as x approaches a is positive infinity because as I approach from the left-hand side and also from the right-hand side, both of them are going up to positive infinity. Similarly, for the second example on the right-hand side, I can say that as I'm looking at the function from the left and also from the right, they're both going down towards negative infinity. However, I don't have a picture, I'll draw one. However, if I had a function that looked like this, a traditional rational function, I'll just draw a simple one. This is the function f of x equals 1 over x. If I want to know what the limit as x approaches 0 is of that function, I can say that it doesn't exist because from the left-hand side, the function is going down to negative infinity, but from the right-hand side, it's going up to positive infinity. Because they're not approaching the same either positive or negative infinity from both sides, the limit doesn't exist. Sometimes a function is defined in a way that it has a vertical asymptote, right? We've seen functions like that. And in this particular case, because the function is not defined over here on the right side, oops, I didn't want that to be red. That's kind of aggressive. Because the function's not defined over here on the right side, we're only going to consider that function from the left. Similarly, in this on the right-hand side, this function is not defined on the left, so we're only going to consider what's happening as we look from the positive side, just depending on what the function is. So sometimes these one-sided limits come into play based on what the function is. So as I mentioned, usually we can have these ideas of graphs going up to positive or negative infinity when we have asymptotes. And here's a perfect example when we have a tangent function. We know that tangent has asymptotes wherever the cosine is equal to 0 because that's where the function is undefined. And so the cosine is undefined at a number of places, right? We can see it from this graph at negative pi over 2, positive pi over 2, 3 pi over 2, etc. We can write this sort of all together in this format, pi over 2 plus n pi, because the period for this graph is n. And so our asymptotes are going to be, or sorry, the period for this graph is pi, and n is an integer, and so all of the asymptotes will be spaced out pi, and then 2 pi, and then 3 pi from the next. If we want to consider what's happening at a particular point, like, let's say, pi over 2, from the positive side versus the negative side, from the negative side, we're going up to positive infinity, right? Over here. And from the negative sign, we're going down to, or from the strike that. Let me start over again. We're going to look at what's happening as we approach x equals pi over 2. As we approach from the left-hand side, where the graph is going up to positive infinity. As we approach from the right-hand side, the graph is going down to negative infinity. So we do have the one-sided limits, but overall we would say that the limit does not exist. We would say the limit as x approaches pi over 2 of tangent x does not exist. Notice that what I'm saying is I'm not necessarily considering from the negative side or the positive side, just overall. Just to kind of reiterate, the notation, the various notations that we can have are all listed here, right? And this is just saying these are all the possibilities of what we can get, positive or negative infinity approaching from left and right. All right, thank you for watching. In the next video, we'll go through some specific examples of how to evaluate limits.